Hello everyone. Before diving into today's topic, we want to take a moment to thank you for your support. Every like, comment, and subscription really makes a difference and helps this channel grow. If you enjoy our content and don't want to miss upcoming videos, subscribe to the channel and turn on the bell to receive all notifications. Among the thousands of exoplanets discovered over the past decades, one in particular has managed to capture the imagination of scientists, philosophers, and astronomy enthusiasts in every corner of the world. K2-18b. This exoplanet, located about 124 light-years from Earth in the constellation Leo, has over time become a sort of modern symbol of our search for life beyond our planet, a new scientific North Star, toward which to direct dreams, questions, and increasingly advanced technologies. It was discovered in 2015 thanks to data from the Kepler mission, a space telescope launched by NASA to monitor hundreds of thousands of stars in search of those faint drops in brightness that indicate a planet passing in front of its star's disk. K2-18b was there, almost daring our gaze, orbiting a red dwarf star called K2-18, a smaller, cooler, and longer-lived star than our Sun. Red dwarfs are the most common type of star in the Milky Way, and for some time it has been hypothesized that they could host potentially habitable planets, although the idea that life could evolve in systems so different from our own has sparked an intense debate between skepticism and hope. K2-18b has a mass about 8 times that of Earth and a radius more than twice as large. These characteristics place it in the category of so-called sub-Neptunes, planets intermediate between Earth and Neptune, for which there is no equivalent in our solar system. And it's precisely this uniqueness that makes it fascinating. It's different, mysterious, and yet somehow familiar. What makes it even more interesting is the fact that it lies within the so-called habitable zone of its star, a region where theoretical temperatures could allow for the existence of liquid water, a key element for life as we know it. But the real breakthrough came in 2019, when a team of astronomers used data from the Hubble Space Telescope to study the composition of K2-18b's atmosphere. To their great surprise, clear traces of water vapor emerged. It was the first time that such an element had been definitively detected in the atmosphere of an exoplanet located in the habitable zone. This discovery had a huge impact on the scientific community. Not only did it confirm the presence of one of the fundamental molecules for life, but it also demonstrated that astronomical observation technologies had reached a sensitivity sufficient to probe the atmospheric secrets of extremely distant worlds. The method used, called transit spectroscopy, involves analyzing the starlight that passes through the planet's atmosphere during transit. The molecules in the atmosphere absorb specific wavelengths of light, leaving a characteristic imprint in the spectrum. It's a fascinating and delicate technique, requiring almost obsessive precision and extreme patience, but it allows us to sniff worlds hundreds of trillions of kilometers away. However, knowing that there is water vapor is not enough to declare a planet habitable, or even less, inhabited. Much more is needed. K2-18b has a thick atmosphere, likely dominated by hydrogen and helium, with extended layers that may be inhospitable to Earth-like life forms. Its surface, if there is a solid surface, could be at pressures and temperatures that would prevent the existence of organisms as we conceive them. Yet, we cannot rule out the existence of a temperate environment somewhere between the upper atmosphere and the core, a kind of internal Goldilocks zone, with stable temperatures, tolerable pressure, and, who knows, liquid oceans capable of supporting the chemistry of life. And this is where the true magic of science comes into play: hypothesis, possibility, imagination informed by data. Astrobiology moves on a fine line between science and intellectual exploration, where every detected molecule could be a biological signature or an unknown geochemical process. In 2023, the James Webb Space Telescope enabled another leap forward. Thanks to its infrared sensitivity, it detected signals consistent with the presence of a highly specific molecule, dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by living organisms, particularly by phytoplankton in the oceans. It is a potential biosignature, one of the few compounds we currently link directly to biology. If confirmed, The presence of DMS on K2-18b would be one of the most significant discoveries in human history. It would imply, cautiously but decisively, that we are not alone. Or at least, that life is a natural phenomenon of the universe, and not a cosmic rarity. Of course, we are still far from confirmation. Spectroscopy can give false positives, signals can be interpreted in different ways, and complex abiotic processes could mimic the signature of DMS. But the mere fact that we can ask these questions, that we can seriously consider the possibility of life on another planet, is already extraordinary. K2-18b also raises philosophical questions. What is life? Does it have to be like ours, based on DNA, proteins, and cells? Or can it exist in radically different forms, immersed in environments that would seem toxic to us? In hydrogen-rich atmospheres, among chemical clouds and exotic seas? If we found life on K2-18b, it would change our place in the cosmos. We would no longer be an anomaly, but a variation on a universal theme. The very concept of habitability is evolving. It is no longer tied only to the presence of liquid water, but to an entire network of complex factors, chemical, thermodynamic, environmental, that can create the conditions for molecular self-organization, replication, and perhaps even consciousness. Future missions like ESA's aerial and next-generation ground-based observatories like the Extremely Large Telescope, ELT, promise to analyze the atmospheres of thousands of exoplanets in detail. But K2-18b will forever remain a pioneer, a watershed moment, a living proof of our desire to know. It is also a triumph of collective intelligence. Behind every data point are dozens of scientists, engineers, analysts, programmers, visionaries. It is the result of centuries of astronomy, from naked eye observations of ancient skies to today's technological giants scanning the cosmos. In an age when we often feel lost amid wars, climate crises, and disillusionment, K2-18b reminds us that we can still dream big. That we can still look to the stars with hope, and that science, when fueled by curiosity and courage, can open unimaginable doors. Perhaps, in a not-so-distant future, a more mature humanity will send interstellar probes capable of crossing the abyss between stars to explore worlds like K2-18b not just with light, but with presence. Until then, we will continue to listen, observe, calculate, and hope. Because K2-18b is not just a point in the sky. It is the projection of what we could become, if only we had the courage to seek.